right, we ready to go? Okay. Neil, we ready? Okay. So following on from our last thermo lesson, we were looking at the enthalpy calculations, and if you guys remember, with those enthalpy calculations, you were heating up a solution, sorry, not a solution, you were heating up water to see how much energy is being released from the burning of, I think, butane gas or something like that. That type of question can be asked another two different ways. The second way they could ask that question is by mixing solutions together. They sometimes call this a neutralization question. So just be in mind, if you're looking through this iPad, they call this neutralization. The last one that they can ask you then is a dissolving question. So you take an ionic salt, you add it to water, and you mix it to dissolve it, and then measure the temperature change. So this can be asked in three ways. You're more or less using the same working and equations. The only thing you have to watch out for is how you read and process the question and pull that information out. Are we okay so far? All right. So in this question here, we are mixing hydrochloric acid and ammonia. So hydrochloric acid and ammonia are my two things that I'm mixing together. They give us the concentration for each solution, and they also give us the volume. So that's really important because that can then tell us the amount that we are dealing with. So we have our acid, our concentration, the volume, our base concentration, and our volume as well. The equation for this, just so you guys are aware, is HCl plus NH3, and those two will neutralize to produce ammonium chloride and water. What does this equation look like? How are you forming H2O? Oh, I see. All right, so yeah, that's what you're forming. That's the general equation. So you're going HCl with ammonia. You're making ammonium chloride as your product, and water. So here's what we need to think about then for that equation. It has a temperature rise of 6.50 Celsius. So that's my change in temperature. And it's a neutralization reaction. So be mindful that they do nickname these neutralization. In the iPad and stuff. They want you to calculate the enthalpy for this neutralization reaction. And you'll be doing that by figuring out the change in the energy, so the energy released from the system. And then that's our heat capacity for water, so that one is our constant. Cool. Right, so if you guys remember, the first thing we're solving for is Q, and we figured that out by taking the mass, timesing it by the heat capacity for water, and timesing it by the change in temperature. And remember, they will give you these equations on the exam, so you don't have to stress about memorizing them. Now remember, when we're talking about mass in this equation, we are talking about the mass of the water, which they say the mass of the mixture is 50. So that is the mass of the water. Because I've taken 25 mils and 25 mils, and I've mixed them together. 25 plus 25 is 50. 1 mil of water equals 1 gram. So that's how I've gotten that number. Do we need me to backtrack? Yes? Okay. So this temperature change is occurring in 50 mils of water. 1 mil of water is the same as 1 gram of water. So if I have 50 mils of solution, I have 50 grams of water. Okay? I also know I have 50 grams of water because I've mixed 25 mils of acid with the 25 mils of base. So 25 and 25 equals 50. So that's how I got the mass of water. Okay? So I would be doing Q equals 50 times, actually let's put the units in there so we can see how everyone's going, times the heat capacity for water. So that's 1.48 grams, joules per grams per degree Celsius. And then I multiply it by the change in temperature, which I've measured as a rise in as 6.5 degrees Celsius. So that's what I'm doing there. I'm going to grab my calculator so we can see our math. Why are you thinking? All right, 50 times 4.18 times 6.5, and I get that this has released 1,358.5 joules of energy. And if we want to convert that into kilojoules, we'll just divide by 1,000. You don't need to, but I find it helpful because we usually think in kilojoules. So that'd be 1.3585 kilojoules is what was released. Are we okay with how I got to that number? Yes, no? No? So 50, 4.18 times 6. So these things all times together, I got that number here. This number is in joules, and I want to change the units to kilojoules. So I'm just dividing it by 1,000 to get to kilojoules. We good now? Yep, okay. So my next thing I need to think about is that my enthalpy, my delta H, is equal to the negative Q value divided by the amount of moles in that reaction. Yeah, so Q is the change in heat. So we have my Q number already, because that Q number is just going to go here. Yeah, change in heat. Or change in energy. So I know that number. I don't know my mole number, though, because that's the N. So I do know the moles because they have given me some information at the top. Now, what they have told me is that we have 1 mole of solution and we have 1 mole of ammonium solution as well. So hydrochloric and ammonium are at the same concentration. When I look at the equation here, they are a 1-to-1 ratio. So they are basically completely the same amount. They are balanced. So if I was to do some math to double check the moles that's being provided from each one, if I want to do, if I did concentration is equal to N divided by V, because I want to find the N value. So I would need to rearrange it. N would equal C times V. So for the hydrochloric acid, N would be equal to 1 moles per liter times, in this case, we are using 25 mils, so we need to divide that into liters. So again, divide by 1,000, 0.025 liters. So the liters cancel out, and my amount is 0.025 moles of acid. So I took that from the volume that was up here, 25 mils. And I just divide it by 1,000 again, so I can get it into liters. Yep, toilet. Let me focus that again. 52, 7, 9, 2, 3. What? All right. So that's the amount of hydrochloric acid. What I'm going to show you is I'm going to also check the amount for the ammonia as well to see which of these two is the smaller of the two numbers. Because whichever is the smaller of the two numbers is what's going to run out first. Yes? So if I was doing the ammonia, C equals N divided by V, N equals C times V. I think so. Let me double check. So N equals the concentration, so it's 1 mole for the ammonia. And the amount is also 25. So what you're going to see is that both numbers are the same. Yeah. So if you did these calculations and one of these two numbers was smaller, you would use the smaller of the two numbers. So if these were two different numbers, say this was 0.02 and this was 0.25, that would be the smaller of the two numbers, and that will run out first for the reaction. Okay. If these were different numbers, the smaller of the two numbers is what I would put in for the N. Yeah, because you would run out of one of your reagents. So you would use the smaller of the two numbers because the reaction would run out of one of your two reagents. What they should give you is whatever they give you should be the same number regardless. So it's perfectly balanced already. So like you run out of the reagents at the same time. So we run out of acid at the same time we run out of base. So I can use 0.25 either way. So I'd plug in my values. Delta H would equal negative 1.3585 kilojoules, and I would divide it by the N, which is 0.025 moles. So I'm dividing that number by 0.25. So I get delta H equals negative 54, and I want to do these three significant figures. So I look at the 3, because that's 1, 2, 3 sig figs. There's a 4 there, so I round down, and I just take 3. And I would go kilojoules per mole as my final answer. And that's it. So you see what I'm saying? It's more or less the same calculation that we did in the previous example when you're heating heating water with a burning fuel. The only thing that changes is how I decode the question. So how I pull the information out. Okay. Keep going. All right. This one here you guys have seen already. So this one talks about experimentally they found a value that was lower than the theoretical one. Explain the differences for these two and how to minimize it. It's exactly the same as the one with the burning fuel one that we talked about, was it last week? You're talking about how energy was lost to the environment and didn't get transferred to the water. We need to better insulate it, that sort of stuff. Okay, let me pull up the answer key so you guys can see it. It was on the Google site. Thermo. Mixing solutions. There you go. Here are the answers. So you guys can see how the points broke down. I think that was question 2 from this 2013 exam. I had to actually search around quite a while for it because they don't ask this one that often. It's quite nice. Here you go. Question number 2, we got the same answer, negative 34.3 kilojoules per mole. If you got the correct calculation with the significant figures and the units and the sign, make sure you have the negative sign on there. That was an excellence point. Yep. Because it's an exothermic reaction. All right. Merit was the correct answer, but you made some error somewhere. So you made a mistake with the moles, or you rounded it wrong, or you didn't put your units down, or you have the sign wrong. It's just like a mistake. That is a small mistake for the merit. Okay. And then the achieved was you calculate the energy correctly. So that's the Q value. Or you calculate the number of moles correctly. So that would be the concentration equation that we talked about. So do all your work and give everything a go, because if we can see that you've done one of the steps correctly, we can give you an achieve point. This is the second part here, which is the part 2. I didn't write any answers down because I figured you guys have already covered it in our last lesson when we were doing the heating of a solution. So conditions weren't at standard. So 1 atmosphere pressure, 25 degrees Celsius. That would be one kind of reason why there's a discrepancy. Or you talked about how it was lost to the environment or the beaker or the atmosphere, the surroundings. Basically, it wasn't transferred to the water, this heat energy. Or you need to talk about how you should insulate the equipment so that way the heat does get transferred to the water and not to something else. This one was strangely only an achieve point. I think this is usually a merit point that will go up to. This is a really old exam. So in the more recent exams, what they do is you've given a reason for the achieved and you've explained the reason, and you explained a improvement technique is usually the merit point. So do keep in mind that some of these exams are different, but that's the idea for that one. Cool. Questions, concerns, comments? All right. So what I would suggest you guys do, Thermo kids, if you're not feeling confident, pages 82 to 89 have these calculations. Keep in mind that they might have calculations for the dissolving of substances, and that's what I'm going to be talking about tomorrow. So you can skip those questions if you want, but you could give them a go. You more or less have learned the theory behind it. It's just pulling the information a little bit differently. If you are feeling confident, you can do the collated questions, often no break too small. And the final choice you guys have is working on ocean acidification, or you can work on organic. Cool. That's me for today. You have the rest of the period to study.